to this AV. Today we're talking about Unit 2, which is basic differentiation rules. And right now for a warm-up, we're going to be back looking at the graph of x squared. This time I have this black line you can see that passes through the point at x equals 1, y equals 1, and another x value I'm choosing right here. Right here I have it choosing 0. I can choose whatever I want, and then it'll spit out this slope right here. And if you're familiar with tangent lines, that's what this should be. If you want to find the instantaneous rate of change at x equals 1, I need to find a point where this black line only hits the graph once. And you could set it up differently, but the way I have it set up, if I actually were to find that point, it's going to have, these are going to be the same values. It's going to end up spitting out a 0 over 0, which is undefined. But either way, if you were to do it the way we've been talking about, taking a limit, so I'll take a value that's really close to 1 on the other side, so this is 0.9, and I get out a 1.9 slope. And then if I take a value that's really close on the other side, so here's 1.1, get 2.1, so you can tell if I'm approaching a similar value from the bottom and the top, you could assume that the slope is 2. But the takeaway is that we want to find an easier way to find the slope, because you're going to have harder and harder questions. So a simple definition of the derivative, and we talked about this one if you watched the last video about Unit 1, but there's a second definition of the derivative which is a little bit more involved. But just what the derivative is in words, it's a function that'll give any instantaneous rate of change for any x that you put into it. People will call it f of x, or f prime of x, y prime, or dy over dx, which is change in y over change in x, rate of change. And you can look at the way either of these functions are. So you would take one point, and then you would take a point with adding some value h, and then find the limit as that h approaches 0. This is a simplified version of it because the bottom is just x minus x plus h. So you would write it as f of x minus f of x plus h over h. And this other version is a little bit cleaner looking, but sometimes it can be harder in context when you're working with it with problems. This, you take f of x over x minus, and then some other point f of c minus c, and you can take the limit as c gets closer and closer to x. Both valid ways of doing it, depends on the question. So now we have some simple derivative rules. There's easy ways, besides plugging a function into this, there's easier ways to find the derivative of any function. So if you have a function that has different terms that are added or subtracted, you can take the derivative of each one separately when you're trying to take the derivative of an entire function. And the derivative of a constant is always going to be 0. These are the two rules that you're going to use in almost every derivative. Another one that you use all the time, the power rule. So if I have x to the c, the derivative of that function is going to be this c is going to go multiply times the x, and then you're going to take the exponent down 1 power. Yeah, same thing written here. So we'll practice a couple here. I think it's easier to just see samples. You're going to have to excuse the computer mouse handwriting. Alright, so if I have x squared, this same rule, we're going to move the 2 out as a coefficient of the x, and then the x is going to be to 2 minus 1 power, which is to the first power. Anything to the first power is itself, so the derivative of x squared is going to be 2x. Then if we go back to that example from the beginning, we can find out what we already inferred, which is that the derivative of x squared at the point 1 is 2, because if I were to plug in the point 1 in this function, I would get 2, and any x that you plug into this function gives you the instantaneous rate of change for this function, which is the point of the derivative. So in this one, we'll just rewrite it because the exponent form didn't stay. So this is 3x to the third plus 2. And remember, we can take these separately, so I'll take 3x to the third. I'm going to multiply this thing by 3, so 3 times 3x. We just move the exponent. Then we take this one, minus 1, so this becomes 3x squared, plus, and then we already said the derivative of any constant is 0, so 0. Now I'll multiply this 3 out. This 3 just stayed on the outside the whole time. So we have 9x squared becomes our answer for the second one. And the third one we'll write down here. This can trick people up. This is literally just the derivative of x. But this is actually the derivative of x to the first power. So we'll move that power over here to the coefficient. So we have 1 times x. You can do this, you can say x to the 0 power. If you remember, anything to the 0 power is just 1, so this becomes 1 times 1, which gives us an answer of 1. The derivative of x is 1. Probably have to know that for your class. So our answers are going to be derivative of x squared is 2x, derivative of x to the third plus 2 is 9x squared, and then this derivative of x equals 1. Then there are a couple special rules. Some classes might go through them and derive the formulas, but most of them you'll just have to memorize. So the derivative of e to the x is e to the x. It is itself. Anytime you have e to the x, its derivative is itself. It's a special property. The derivative of natural log of x is 1 over x. And then all of the trigonometric functions. So the derivative of sine of x is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. Derivative of cosecant is negative cosecant x times cotangent of x. Derivative of secant of x is secant of x times tangent of x. And derivative of cotangent of x is negative cosecant squared of x. The more you do practice problems with these, the more they're going to come naturally. If you take a year-long class in calculus, you'll have them memorized by the AP test. I was overwhelmed by it, and I memorized them in time. But that's it for derivatives and basic derivative rules. Thanks for sticking around.